Okay, I hope you can all see my board. Again, please mute your mic. I hear water running. I don't know if somebody is washing the plates and also listening to the lecture or what's happening. Okay, so we can hear your background noise. Please mute your mic and you can carry on washing the plates. Okay, so let's look at number 14 from the homework. I won't do all of them like I said. I will send you the memo. If you had any problems, then you can see how to do it. But the exercise also has answers to it, so you can see if what you did is the right thing. So number 14, we have 5 to, just put this. Okay, we have 5 to the power of log base 5 of 8. This, okay, hold on. Okay, background noise, please. You're playing music in the back. Just mute your mic. Thank you. You can still hear music in the background. Please mute your mics. Put it on mute. Okay, somebody's music is still playing in the background. Please mute your mic. Thank you. Okay, so we have 5 to the power of log base 5 of 8. Now this one, we just need to use the law that says if I have an exponent raised to, if I have a base raised to an exponent, which is a logarithm, and it happens that the base over here is the same as the base of the logarithm. So we have base of the exponent is equal to base of the logarithm. Then what you have is the answer is just equal to the argument of the logarithm. Okay, so what this means is I have 5 here. This is the base of the exponent, and 5 is also equal to the base of the logarithm. Then this is just equal to 8. Now, I know it's listed as one of the laws that you have, but you can actually prove that this is true. Okay, so you can look that up and see how it is proved, or like with the other laws, you can just take it. That is the way that it is. So anytime I have a, my exponent of a is log and the base is a, then whatever I put here, I put x plus 2. This is equal to x plus 2. I have a log base a. This person who just does not want to mute their mic. I don't know why. Okay, whatever I put over there, it doesn't matter. I could even put another log 5 if I wanted to. This is just equal to log of 5. So as long as I have a base of my exponent, which is equal to the base of the logarithm, then that is equal to whatever my argument is equal to. Okay, so we go back to number 14. Let's see. So we were given 5 to the power of log base 5 of 8. This is equal to 2 to the power of, 2x. Now here I say that the base is 5 and the base of the logarithm is 5. That means this is equal to 8 and this is 2 to the power of x. 2x. Then you solve this, divide by 2, divide by 2, then you get x is equal to 4. Okay, then number 16. Okay, let's look at number 16. We have x is equal to log base 2 of 7. This is being multiplied by log base 5 of 2. Now here there's no law that says anything about combining logarithms when you multiply them. So the only thing we can do is change the bases so that the bases are the same, and then we see if anything will cancel. So I'm going to change the base of this one to base 2, okay, because the base there is 2. I can change the second one, I can change the first one to base 5. It doesn't matter as long as there is the same base. You'll see some things will cancel. Okay, so this is log base 2 of 7, and then I'm multiplying this by, remember how we changed the bases? I put log base 2, log base 2, then the argument goes to the numerator, and then the base goes to the denominator. Then here in the numerator, this is equal to 1. So I have log base 2 of 7 multiplied by 1 over log base 2 of 5. So you know how to multiply fractions. This is over 1, numerator times numerator, denominator times denominator. This gives me log 2 7 log base 2 of 5, and this is just equal to log base 5 of 7. We did an example yesterday where the base was e, and I showed you how you can get rid of your base over there and then rewrite it like that. So revisit that one if you don't know how I got this. Then I think I will look at number 22. Number 22, we have ln of x squared is equal to ln of x. Now the whole thing is squared. So again, this is a quadratic equation. You should be able to see that. Now first thing you should do is this 2. You can bring it down. It is the exponent of the argument. It can come down. So you have 2 ln of x is equal to ln of x squared. All right, then what you do is you let y, so we let y equal to ln of x. Okay, so don't let x equal to ln of x because there's already an x there. You'll get to a point where you get the value of x and then you think you're done, but you're not. So there's other letters to pick one of them. So you have 2y is this ln of x. Instead of writing ln of x, I put y. And on the other side, instead of putting my bracket over here, I put y squared. Now this is a very simple quadratic equation to solve. You bring everything to one side, y squared minus 2y. This is equal to 0. Then you factorize, y is a common factor. So this is y minus 2 is equal to 0. two terms are multiplying and the answer is 0, it means the first one is 0 or the second one is equal to 0. Okay, for the second one, this means that y is equal to 2. But remember, in the question there was no y. I'm the one who put y there, so I need to go back and unsubstitute. So over here I said y is equal to ln of x, so I'm going to replace this y with ln of x. So I have ln of x is equal to 0 or ln of x is equal to 2. Now ln of x means log to the base of e, so I can rewrite it like that. This is log base e of x is equal to 0. Then I write this in exponential form. It is base to the power of exponent is equal to the argument. So x is equal to e to the power of 0. So my base, exponent, argument. And then with this one as well, I do the same thing. This is x is equal to e to the power of 2. Now here, x is equal to e to the power of 0. Anything except 0 to the power of 0 is equal to 1. So my first solution is 1. And then this one, when x is equal to e squared, you just type in on your calculator, you get x is 7.389. Okay, those are your two solutions. I will do just one more, number 27. We have log base 3 of x squared minus log base 3 of x squared. This is equal to 3. So first thing I always do is this 2, I must bring it down. So I have log base 3 of x squared minus 2 log base 3 x, and then the minus 3, or the 3 comes to the other side and then it's minus. So I hope you can see again that this is a quadratic equation. So I let log base 3 of x. This time I'll pick a different letter because I'm allowed to. Why not? Let it be equal to w. Then I have w squared minus 2 times w. So you can see this is w over here. The only thing not there is the squared. That's why I have w squared. And this part here is w. So I have 2 times w. And then minus 3. This is equal to 0. Now this is a quadratic equation that you can factorize. So you know how to factorize. I open my brackets. This is equal to 0. Then the variable is w. Then I look for two numbers that multiply to give me minus 3. And when I add the two numbers, the answer is equal to negative 2. So the two numbers are negative 3 and positive 1. So I put them there, negative 3 and positive 1. Okay. Then I solve. I will get w minus 3 is equal to 0. And this means that w is equal to 3. And for the other one, w plus 1 is equal to 0. This means that w is equal to minus 1. But remember, w is not in the question. It's something that I let. So I need to go back and solve. So w, we said, is log base 3 of x. And the first w is 3. So this is 3. To solve this one, I write it in exponential form. It is base exponent is equal to the argument. So that means x is equal to 3 to the power of 3. And this is just 27. When you do the same thing with the second solution, we say w is log base 3 of x. And this was equal to negative 1. That was our second solution. Now we solve it. Our base exponent is equal to the argument. So I'll have x is equal to 3 to the power of minus 1. This means x is equal to 1 over 3. Okay, so the others are not much different. You should be able to solve it. If you were not able to, again, I'll send you the solutions and then you can check if what you did is correct, or see if what you got is solutions in the book, then you can see where you went wrong. Okay, so today we look at sketching exponential and logarithmic curves. I know some of you say this is difficult or you couldn't understand it, but it's actually not. Okay, this logarithmic and exponential, or exponential mainly. Okay, I'm waiting for my screen. I don't know what's happening, but it's coming. Okay, now exponential functions, these are the easiest functions that you can draw because they all have the same shape. Okay, now our exponential function, or let me say exponential graphs, they look like this. You have y is equal to a to the power of x. So you've done graphs before. For example, with lines, you had y is equal to mx plus c. That is what a line looks like. It has that formula. Now exponential graphs, they have that formula. Plot them on the x and y axis. They sound behind my voice. I hope it's better now. Okay, I think it's better now. Okay, so the way to plot them is they all look exactly the same. Okay, they have the same shape. Now the shape that they have, it's one of two shapes. Either it looks like this, and this point here is always equal to 1. Always means all the time. There is no time where you sketch a graph like this where it does not pass through the point 1. Maybe if you've added something over here plus, I don't know, something you can add there, then it will change. But when it is in this basic form, it must pass through 1. So this is the first way that it can look. Okay, so this is the first way. And then it can also look, like this. This is still the number 1 over here. So this is your x-axis and that is your y-axis. These are the only two possible ways that you can draw the function y is equal to a to the power of x. Now, how do you know which one it is? Here you have a, which is bigger than 1. So you have a positive number that is bigger than 1. Let's say, for example, a is equal to 5. This is how your graph will look like, okay? And then for the second one, if you have a number between 0 and 1, let's say half, for example. So this could be a graph y is equal to 2 to the power of x, and then this one, y is equal to half to the power of x. I'm sure you can see that these graphs, they are related in some way, or if you start with this one, you can describe it like if somebody is in primary school and they ask you, how did you get from this graph to that one? Somebody will say, I just reflected this graph along the y-axis and then I get this one. So if my y-axis over here acts like a mirror, what you will see is this. Let me just change this. Okay. If it acts as a mirror, you will see I will get this graph over there. And then this one in red is exactly the same as the one that I have over there. Okay, I don't know what's happening with the green. Let's hope it holds on for the rest of the lesson. Okay, so the one in red is just a reflection of the one in black over there. And in the same way, if I reflect the one in red along the line, along the y-axis, I will get the one in black, So it's like they are a mirror reflection of each other in the y-axis. So here, the first one in black, this is when you have a positive number that is bigger than 1. Over here, you have a positive number because it's bigger than 0. Any number bigger than 0 is positive. You have a positive number that is less than 1. So we don't draw exponential graphs when your base is equal to 1, because if your base is equal to 1, then it's just a straight line, because 1 to the power of 1 is 1. 1 to the power of 100 is 1. So it's just a horizontal line. Okay, and with negative terms, we don't have the exponent, we don't have a graph for them, because when you raise it to the power, it changes from positive to negative, just like that. Okay, let's see, I'm trying to scroll up. So let's see an example of how we can draw a graph. So go back to black. Now let's say I say sketch the graph y is equal to 3 to the power of x. Okay, this is the simplest question you can ever get in a test. So what you do is you will just take your graph like this. Now 3 to the power of x, we said there are only two possibilities that your graph can be. It'll either be this one here, the one in black, or it'll be this one over there. So first thing you have to decide which one is it. Now I look at my base. My base is 3. 3 is greater than 1. 3 is greater than 1. And that means that it'll be the first one. Okay, so if it's the first one, that means it starts slowly, it's very close to 0, and then it cuts the y-axis. The y-intercept is 1. It is always equal to 1, and then it continues, it's increasing very fast. This is x. So this is my graph, y is equal to 3 to the power of x. Now the hard part, or the tricky part, comes in when I ask you to draw two graphs on the same, or two exponential functions on the same graph. Now let's say I also ask you to sketch y is equal to, let's say, 10 to the power of x on the same graph. Now I know the shape of y is equal to 10 to the power of x is also going to be like that. Okay, that is the general shape. Now, how is it in relation to 3 to the power of x? Now, remember what 10 to the power of x means. That means you're multiplying tens. So you keep multiplying 10, multiplying 10. Now, 10 to the power of x gets bigger, quicker, or it grows. It's much bigger than 3 to the power of x, in other words. So it's like it's going to infinity faster than 3 to the power of x. Because if you look at your graph here, this is just increasing. It's going up, up, and it's going all the way to infinity. Now it's like you're asking yourself, which one is going to reach infinity first? Now 10 to the power of x is going to reach to infinity first. So here, it'll go, it still passes through 1, because all the exponential graphs pass through 1. But it's like it's getting to infinity faster. It's becoming a straight line faster, because y to the power of x is the one that reaches infinity the fastest, because it stays at the point 0, but it's already at infinity. But this one, it needs to get x is equal to 0 point, x is equal to 0 point something, x is equal to 1, and so on, something like that. And then on this side, you will see that it is below the line of y is equal to 3 to the power of x. So this one is y is equal to 10 to the power of x. Okay, and you just need to keep that in mind You cannot see that, but it's this one here. Just draw a line. Oh dear. Okay, so this graph is just y is equal to 10 to the power of x. So the bigger your base, the closer the graph will be. Somebody's mic. So the bigger your base is, the closer it is towards the y-axis. Let's look at another example where we are comparing graphs. Let's see. Let's say I say draw y is equal to 3 to the power of x and y is equal to 2 to the power of x. Okay, now here again, first thing you need to decide is which one, which of the two graphs is it, or what is the shape? Is it like this or is it like this? Now this graph over here is increasing and this one is decreasing. Okay, so you look at what is happening when you go in that direction. When you go in that direction, it's like you're going up a very steep hill. And this one, when you're going in this direction, it's like you're going down a hill. So the graph is decreasing. Okay, so here, when our base is greater than 1, then it is this graph over here. This graph over here. Now when the base is less than 1, between 0 and 1, then I will take this one. So I look at my bases here, it's 3. So 3 is going to be this one here. And 2 is greater than 1. So 2 is also going to be that one over there. So I just have to fit them on the same graph. So I draw my axis. Now remember, the bigger base must be the one that is closer to the y-axis on the positive side of the y-axis. And it must be closer to the x-axis on this side. Okay, so on this side, the bigger one is closer to the y-axis, so it's getting closer to that one. And on this side, it's closer to the x-axis. So just draw them. The first one, so this is my x-axis, that is my y-axis. And this one, let's say I make it y is equal to 3 to the power of x. Then for the second one, I say that 2 is less than 3. So 3 must be further away. They must both pass through this point 1, but it must be further away from the y-axis than this graph over here on this side. So on this side, it must be further away. So when I draw it, the shape is similar. So it looks like that. And then on this side here, it must be on top, or it must be, let me say that again, label. This is y is equal to 2 to the power of x. On this side, the bigger one must be closer to the y-axis. That's why I put the 3 here. 3 is closer to the y-axis than 2 to the power of x. Then on this side, the bigger one must be closer to the x-axis than the other one. That is why I will draw it like that. They are both getting closer to 0, so maybe it's not so clear, but they're both going down to the x-axis, but it's just that the red one is above the black one, and that is how you sketch it. Okay, so right now I want you guys to try one. We have a 2-hour lecture, so I don't want to talk the whole time, so I'll give you time to try some, and then after like 2-3 minutes, then I will go over it together. Now let's say I tell you to sketch y is equal to 10 to the power of x and y is equal to 5 to the power of x on the same graph. Can you quickly try that? I'll give you 2 minutes.
Ma'am, your mic is on mute.
Oh, sorry. Can you guys hear me now? Okay. So with this one, let's say I give you this graph. This is X and that one is Y. And then this one here, you must always label it. Okay, so you label your X and the Y axis and then you label the point 1. Now on the same graph, what I want you to do is sketch the graphs y is equal to 2 to the power of x and y is equal to 5 to the power of x. So can you do that? Take a few minutes and then see if you are able to figure it out. Remember the principle in the first quadrant, which one must be closer to the y-axis, and then in the second quadrant, which one must be closer to the x-axis. Okay, then try and combine all three on the same graph.
No.
Yes.
I just want to clarify something. In your
Yes.
second quadrant, the one
Yes.
with, say for instance, there's 2 to the power of x and 5 to the power of x.
Yes.
The bigger one is the one closest to the x-axis.
Yeah. Yes.
Okay.
So in the first quadrant, bigger one closer, and then in the second quadrant, the bigger one is also closer to the x-axis. Okay, so whatever quadrant it is in, it wants to be closer to first y and then the second one x.
Okay, ma'am.
Okay, so try and draw those two, and they must all relate to each other in that way, that if one is bigger than the other, then in the first quadrant, it must be closer or further away in both quadrants.
And ma'am, do we draw it on the same set of axes
Yes,
you just showed
yes,
us?
yes. Otherwise, it's very easy because you'll just do this like that, and then you are done. So it must be on
Yeah,
the
but I
same.
mean with the one with the previous.
The one with,
graph.
no, this one here, the one in red with 3 to the power of x. So I
Yeah.
must see 3 graphs over here. I must
Okay.
see y to the power, y is equal to 2 to the power of x, y is 3 to the power, or y is 2 to the power of x, y is 3 to the power of x, and y is 5 to the power of x
Okay, ma'am.
on the same graph.
All right.
Okay, were you able to figure it out? Okay, let's do it together, and I hope you tried it. It's very important that you try these questions. That way you learn more. Somebody talking, yes.
I have a question.
Yes,
How is it my graph? You have
I cannot hear what you're
my
saying.
question is why I'm asking that if I have y equal to power minus x,
Yeah,
will my graph be opposite the
if you have y is equal to,
2 to the power of x? You
2
have
to
it
the
here, right?
power of, hey, you're breaking up.
Why I'm saying
Yeah,
uh, most here we have 2 to the y equal to 2 to the power minus x, power of x.
yeah.
So we have y equals to the power of minus x. The graph will be opposite of the
The graph will be the same as y is equal to half to the power of x. And I said that one will look like it's reflected in the y-axis. So y
oh
is
yeah, it will be
equal to 2 to
reflected.
the power of minus x is half to the power of x. But we'll look at those ones just now.
Okay.
Okay,
Okay, thank you.
so let us do this one. So I will start with 2 to the power of x. All right. So 2 to the power of x, I need to decide what is happening in the first quadrant. Okay, I'm hearing a lot of feedback in the background.
Now it's anyway.
Okay, please mute your mic.
Okay.
Okay, so I'll start by drawing y is equal to 2 to the power of x. Now in the first quadrant over here, I need to decide, is it closer to the y-axis compared to 3 to the power of x, or is it further away? So to do that, I look at the base when 2 is smaller than 3, so it must be further away from the y-axis compared to 3. So I will draw this one in black. So it must be further away. So something like that. Shouldn't be too far away because 2 and 3 are not that far apart. So that's in the first quadrant. Then in the second quadrant, we say that it must be, I must decide which one is closer to the x-axis. The bigger number is the one where the bigger base is the one that is closer to the x-axis. So this one in black must be, oh dear, this one in black must be further away. So that's what it will look like. Okay, so again, in the first quadrant, I had to say which one is bigger, 2 or 3, or which base is bigger, 2 or 3. 3 is bigger, so 3 must be closer to the y-axis compared to 2 to the power of x. Then in the second quadrant, the bigger one must be closer to the x-axis. That's why the one in red is below. Then with 5, I look at 5. 5 is bigger than 3 and 2, so it must be closer to y-axis than both of them. So I'll draw this one in red. So I'll put it somewhere here. Okay, and then I go to the second quadrant. In the second quadrant, it is bigger than both of them, so it must be closer to the x-axis compared to both of them. So there, sorry. So it must be closer than both of them. And they all pass through the point 1. And this is the graph y is equal to 5 to the power of x. That is how you draw them. So you can draw them quadrant by quadrant, but when you draw it, I want to see a smooth curve. It's easier to do it with a pen and paper than it is here on the screen. So with yours, it'll look smooth. The shape must, all the shapes must look like this nice smooth curve, getting closer to the x-axis over there, and over here it's increasing exponentially. Okay, so it must have that nice smooth shape, and it must be getting closer and closer to the x-axis. So here we call the x-axis an asymptote. Now, asymptote just means a line that a curve is getting closer and closer to, but it never actually cuts it. So here you can have a vertical asymptote. It's getting closer and closer to the line, but it'll never actually reach it. Okay, so that's what an asymptote is. Then we look at the other scenario where we have, let me go back to black. We have y is equal to half to the power of x, for example. So like the other guy said, this is just 2 to the power of minus x. So when you get a question like this, you must know that I can rewrite it in this form. And when I rewrite it in that form, then I should know that the general shape is that one. So this is my x-axis, that is my y-axis, and this point over here is always equal to 1. That is what it looks like. Okay? And then I'm trying to scroll up. Okay. Now with logarithmic functions, the way we get them is by reflecting an exponential graph. So you have a graph like this one. Let's see, this is your exponential function. Here I have x, there I have y. This is y is equal to a to the power of x. Okay, and then I ask you to reflect this. Now the reflection that we do is not just any reflection. This is reflection along the line y is equal to x. So when you want to draw a graph where the log of that graph is a, to do that, what you do is you must reflect it along this line. Now this line here is the line y is equal to x. Okay, so it is always equal to that line. It is not any other line when you want to draw the graph of the logarithm. So this line y is equal to x will act as a mirror. So you draw a reflection. I'm sure from high school you did how to draw reflections. Now we know this point here is always equal to 1. So when I reflect it with my mirror over there, it will reflect on the point 1. Then if you look at what is happening here in the, or maybe let's start over here. There's no part of the graph y is equal to a to the power of x in this quadrant. So when I reflect it here, nothing will also be there. Then in the second quadrant, you can see it is getting closer and closer to the axis. So in the reflection, it must also be getting closer and closer to the axis until it gets to 1. Then this part over here, it's increasing, it's going up. So here it'll also follow the same pattern. So it is also increasing and something like that. So you're just drawing a reflection. You'll do a better job in your book. Okay, so this is the graph y is equal to log base a of x. Okay, so first thing you want, if I ask you to draw this one, what you can just do is draw the same graph with base power x, and then you reflect it along the line y is equal to x. Somebody is training. Okay, so that's how you do that one. Let's look at some examples from your notes. Okay. Just hold on. Okay, in the notes I don't really see a lot of questions where you have to sketch logarithms. Okay, maybe number 3. This is exercise 3.7.4, where you have to sketch this one. So we are on exercise 3.7.4, and then if we look at 3.1. 3.1 says we must sketch this. Y is equal to 10 to the power of x. Y is equal to 1 over 10 to the power of x. And also y is equal to log of x. We need to sketch all 3 of these on the same graph. Okay, so to do that, you just need to remember what we said about exponential graphs. First, you must pick or decide which one is it. Now, these graphs are all related in that this one, 10 to the power of x, it'll open up like this. And then 1 over 10 will open up like that. And then log, here the base is 10. If the base is not written, I just have to reflect along the y-axis, and then I'm reflecting this one here, so it'll look something like that. Okay, so it's like they're all reflections of each other in some way. So let's do that. Let's draw them. Okay. Here is my x and y axis. So I will start with 10 to the power of x. Now 10 to the power of x, an exponential equation, must start there next to its asymptote, and then it has that shape. So whatever I have, any number which is greater than 1 to the power of x, this is the general shape, and it passes through the point 1. Then I must label my graph. This is 10 to the power of x. Then this one here, 1 over 10 to the power of x, we said it's a reflection of 10 to the power of x along the y-axis. So it's like my y-axis is my mirror. Then everything I have here, I must reflect it to this side, and it must be symmetric and look like a reflection. So I will use orange here. So when I reflect it, this is what it is going to look like. In this positive x-axis, that is also an asymptote. Then this is y is equal to 1 over 10 to the power of x, or it's the same as 10 to the power of minus x. Okay. Then the last one, log of x. Remember, log of x is the same as log base 10 of x. Okay, so I must reflect the graph that had a base of 10. So this one here is the one that I'm going to reflect. So if I said log of base 1 over 10, I must reflect the exponential one that had a base of 1 over 10. Okay, so here in my logarithm, the base is 10. So this is the one that I'm reflecting. And the mirror that we use for reflecting in that case is the line y is equal to x. That is always the mirror. Okay, just like with these two, the orange and the black one, the mirror is always the y-axis. In this case, the mirror is the line y is equal to x. So I'll draw my mirror in red. So dotted line to show that it is my mirror. And then I will use blue. Okay, so you draw a reflection. You know how to do that. So this number here is 1, so it must also pass through the number 1. And then on this side, it is getting closer and closer to the x-axis. And when I reflect this x-axis, this is the axis that it becomes. So on this side, it must also get closer and closer to the y-axis. Okay, so this is what it is going to look like until it cuts the x-axis. And then on this part here, you can see it is increasing, it's getting away from the line. So even on this side, it must be going away from the mirror. The line is this one here. So continue, we're just drawing a reflection. Okay, so it's going, this part here, it was going up, moving away from the line, the mirror. So even the reflection must also appear to move away from the mirror. Just like when you see yourself in the mirror, you go closer to the mirror, your reflection seems like it's moving closer to the mirror. You move further away from the mirror, your reflection also moves further away from the mirror. And then you just label it. This is y is equal to log of x. Is that one fine? We have comments on that one? No, this one can be a little bit tricky, but it's not too difficult. Okay, if not, then 3.2, let's do that one. This is still exercise 3.7.4. Okay, 3.2, you are told to sketch e to the power of x and ln of x. So y is equal to e to the power of x and y is equal to ln of x on the same graph. So I'll give you 2 minutes. Go ahead and try that one, and then we'll see if you are correct. Okay, so I must see the axis labeled, x-axis, y-axis, the intercepts, the 1, it must be showing clearly. So those are the things that go for marks. The x-axis are labeled, the intercept is clearly labeled, and then the shape must be correct. So it must be a nice smooth curve. You don't join your points with a ruler. With reflecting, what don't you understand? I'm not sure. Okay, the rest of you can continue. Let me just try and explain reflecting again. Let's say I have a mirror over here. If I have this line over there, this is my mirror, and I want to reflect it, this is what it is going to look like. The distance from there to there is the same as the distance from there to there. So just the way you see yourself in the mirror, that's how it works. Okay, so if you're fine with reflection, I'm just answering somebody's side question, so continue until you're done. Okay, so if I have a mirror here, and then I draw this line, and then I say you must reflect it, the reflection is going to look like this. This is what the reflection looks like. The distance from there to there must be the same. Okay, my reflection isn't so good, but that distance, it must be equal. The distance of every point must be equal to the distance of every point on the reflection. Okay, so that's basically what reflection is. When you say, do they use the same formula? What do you mean? Okay, so this distance must be equal to that one. This distance must be equal to that one. And the pattern that this graph is following must coincide with this one here, if you will. Okay, let's look at that one. I think most of you are done. We're supposed to draw ln of x and e to the power of x. So we have y is equal to e to the power of x and y is equal to ln of x. Now remember, the first thing I must decide is for this exponential one, I must say, is my graph like this or is it like this? To decide that, I look at the base over here. If the base is bigger than 1, then I must pick this one over here. So here my base is bigger than 1. And this one, my base is less than 1 and greater than 0. So it's between 0 and 1. Okay, so when I look at E is 2.7 something. Okay, so that is bigger than 1. So the shape of e to the power of x is going to be this one over here. So what I do is I draw the curve, and then this is the x and that is the y. Now we said e to the power of x has this shape over here, like that. This point here is always equal to 1. The y-intercept is always equal to 1. So this is y is equal to e to the power of x. Then ln of x, remember ln of x is log base e of x. So I'm plotting the logarithm. To get the logarithm function from the exponential function, what I do is I reflect this graph over here along the mirror y is equal to x. So I need to draw the mirror y is equal to x. Put it there in yellow. So I'm drawing it as a broken line to show that I'm just using it as a mirror. Now, after that, to draw the reflection, this point here is 1 and it lies on the y-axis. When I reflect the y-axis along the mirror, it becomes the x-axis. The point will become there, will go there, and that value is 1. Then what I do is I look at the distances, these distances over there. They must be the same in the reflection. So it's getting closer and closer. So that is what it looks like. And then over here, it is moving away from my line of reflection and it is going up in that way. So my reflection must also move away from this yellow line and move up like an exponential curve. So to do that, oh dear, to do that, this is what it will look like. Okay, so try and keep the spaces over there, like that space, try and keep them the same in your reflection. Okay, so it's much easier to do in a book than on a screen, like I said. Okay, so that is how you draw it. And then after you've drawn it, you label it. This is y is equal to ln of x. So if you have the exponential function to get the logarithmic one, remember the base of the exponential function and the logarithmic function must be the same. That's how we get the reflection. If I give you log base 5 and then you have 3 to the power of x, those are not reflections of each other because the bases are not the same. So the base must be the same. Okay, right. Then let's look at the next question in your book, in the notes. Log base 2 of x and log base half of x. Now here you can see that the bases are not the same. These are two different reflections of two different exponential curves. So what you can do is you draw 2 to the power of x reflected, draw y is equal to half to the power of x, and then reflect it. Okay, so can you try that 2 minutes? Let's see if you're able to do it. Okay, so the question, let me write it down. You don't have the notes. You have to sketch log 2. This is y is equal to that, and y is equal to log base half of x. Now these two are not reflections of each other. This one is a reflection of y is equal to 2 to the power of x. And this one is a reflection of y is equal to half to the power of x. So remember that. So you can start by drawing 2 to the power of x and half to the power of x, reflect them, and then see how to draw your log functions. So 2 minutes, please try that one. It's very important that you try it on your own. If you're asked to draw the exponential function, then you must label it in exponential form, not in logarithmic form. I hope that answers your question. And then must you draw y is equal to 2 to the power of x? Yes, it's always good to draw them just so you have an idea of what it is you've drawn. No, I see somebody submitted a picture. No, that is not correct. Maybe one of them is correct. Okay, this picture here is what I drew the first time. Why are you sending us that picture? That is 2 to the power of x, 3 to the power of x, and 5 to the power of x. Why are you sending that picture? I thought that was your solution for this one. Okay. Okay, with the question, somebody asked, what if it says y is equal to 2 to the power of x plus 2? I'm sure you did translations in high school. Y is equal to 2 to the power of x. You will draw the graph the same way, and then you move it up 2 units. That means each point moves up 2 units. So it'll still look, the shape doesn't change, it just moves up 2 units. That's how you'll graph that one. Okay. So it's a translation. You move every point 2 units up. Okay, because math error. Then it's because if you look at the reason why it's giving you math error for log is because if you look at the graph that I drew, my x values are only positive. My graph, when I draw it, it's in this region. There are no x values like that. That's why you're getting a negative. Oh, that's why you're getting a math error, because my graph is only defined from 0 to infinity. I didn't have any part in the third quadrant. Unlike the exponential function, I had all the x values from minus infinity to that one. It went like that. So any x you pick, I pick a negative x, I got an answer. I pick a positive one, I pick 0. But with this one, if I look at the graph, if I want a negative x, there is no graph there. So that's why it's giving you a math error. So your graph for logarithmic functions is only from 0 going that way. That's why you're getting math error. Okay, let me just clean this one. Okay, so somebody was asking, do I need to draw, let me just put the question up here. Do I need to draw 2 to the power of x and half to the power of x? Yes, that is like you're working. Okay, so you need to show that in your, you need to show that this is how I got that one. Okay, and I always say some of you, you're very smart. You can already tell what the graph is, so you don't always have to show it, but let us just show our working as much as possible. Okay, so I say to draw, which question is it now? 3.3. Okay, this is 3.3. So the first one is, is that question? Okay, log of x base 2. So log of x base 2 comes by reflecting 2 to the power of x. So I can draw the graph y is equal to 2 to the power of x. And we said I need to decide which one of the two graphs it is. Either the one that is increasing, are you going up the steep hill, or are you going down the steep hill? And you're going up the steep hill because 2 is greater than 1. So this is what it looks like. Okay, so this is my x-axis. Always label your x-axis. This is the point 1. Point 1. Okay, and this is y is equal to 2 to the power of x. But the question asked me for log of x base 2. So I need the mirror y is equal to x. Remember, this mirror is a specific mirror. It is not any mirror you just want to use. It is always this mirror over here. When I want to go from exponential to logarithm, it is always this mirror. Then I draw the reflection. So here, something like that. And this point over here, the reflection of 1 there is equal to the reflection of 1 over there. So this one is y is equal to log base 2 of x. It is a reflection of that graph over there. So I will try and draw all 4 on the same graph. Then the next one we have is y is equal to log base half of x. Now log base half of x is a reflection of, let me use another color, green. It's a reflection of y is equal to half to the power of x. Now half to the power of x is also a reflection of this one. So you can see 2 to the power of x is like our main function, and then I reflect it in different ways to get the other ones that I'm asked to do. So half to the power of x, we said half is less than 1, so the graph will look like this one. So it goes something like that, and it gets closer and closer to the x-axis. Okay, so it's a reflection. You can see this graph over here in black is getting closer and closer to the x-axis. So the same thing must be happening in the reflection. So over here it's increasing, it's going up. So on this side of the y-axis it must be increasing. So when I'm going from two exponents where one is minus 1 power of the other one, then what I do is just reflect in the y-axis. Okay, but now I want log base half of x. Okay, this one is tricky to draw because of my pen, but all I am doing is reflecting along this red line over here. That's all I'm doing. So you look at the graph in green, this is your mirror, and then reflect it. That's it. Okay, so I'll pick a different color. Let me say blue. Okay, so I can start at this point on the mirror. Just like when you are touching your hand on the mirror, your hand reflected is exactly at the same position where you are touching your hand. You won't see yourself touching the mirror at one point and then your reflection is touching the mirror at another point. That doesn't happen. Okay, so they both touch the mirror at the same point. Then you can see the way it's reflected. It goes something like this, and this point, that's where they are cutting. We'll draw a better graph, and then it's also passing through 1 over there, and then it continues like that. So that's what I'm doing. I'm just reflecting. So start at the point where you're touching the mirror, then you see, okay, from this point here, the green one is going down closer to the y-axis. So maybe the way I drew it is not so good. Let me try again. Okay, let me try again. So you can see the green one is getting closer and closer to the y-axis, to the x-axis. So the reflection must also get closer and closer to the y-axis. So start at the point where they are touching, where your hand is touching the mirror. That's where you start. And then you say, okay, in the reflection this side, and the reflection and the image cannot be on the same side of the mirror. That's impossible. When you see yourself in the mirror, there's one of you on one side of the mirror and the other you is on the other side of the mirror. You cannot both be on the same side of the mirror. That's impossible. Okay, so we said it's getting closer and closer to the x-axis over there. So the reflection of the x-axis is the y-axis. So this one must also get closer and closer to the y-axis. Okay, then it cuts this one in black. So it must also cut its reflection somewhere. Let me see, how do I draw this one? Okay. Am I doing this correctly now? Yes. Okay, so it must cut it must go through the point 1 because that is where the reflection is, and then it must continue like that. So you try and draw a very nice reflection. Okay, so start at the point where they are meeting on the mirror. Then you see, okay, it's getting closer to the axis like it's doing over here. So even that one must get closer to the axis. Now this point here, which point? This point here is actually that point there. Because of my drawing, it doesn't seem like it, but it cuts this one in the mirror. So on the other side of the mirror, it must also cut it. Okay, so the question was actually just asking us for the one in blue and the one in orange. This is y is equal to log y is equal to log base half of x. So then that is my working. I can redraw it, and this time I only draw the one in blue and the one in orange. So let me draw my axis. Okay, so this is my x-axis. This one is my y-axis. Then the one in blue looks something like this. Let me use blue. The one in blue, it looks something like this. Then the one in orange looks like that. And they are both passing through the point 1 over there. Then the only thing left is for me to label them. The one in blue, this is y is equal to log base half of x. And the one in orange, this is log base 2 of x. Okay, and then I am done. So it is just reflecting. It's a little bit tricky, but if you practice, I'm sure that you can see how to get that one. Let's do another one, or you guys do another one. I'll erase this. Okay, question 2 in 3.7.4. Can you try that one? I think we've done all the difficult ones, or maybe I'll leave that one for you to do as homework because it's not too difficult. Let's look at number 4. With number, yes, yes.
Before you move on,
Yes.
going back to the one you just did,
Yes.
the graph log half base log base half x.
Yes.
How it there where you plotted it?
This second drawing here,
Yes,
I just drew the orange one. If you look at the orange one here, I redrew it over there. So it passes through one and then it's increasing something like that. So I was trying to draw, what I was basically doing was drawing this same diagram, except I don't draw the green and the black one. That's it.
no,
So it's not a, yes.
so the green one you drew in the first that's half
The
to
power of x.
the power of x. Yes, that's correct.
Yes.
Now,
Yes.
if you reflect that one,
Yes.
where is it?
It is the blue one. The
Do you
green
still
one and the blue
reflect
one.
it behind y equals x?
Yes, I reflected it with this red line. That's why I say they're both touching the mirror over here. Can you see that?
Now, how is it reflected if it's still in the same?
No, no, it's not. The part that is reflected is not the same part that is inside the mirror. Let me just see if is my screen still showing?
Yes, ma'am.
Okay, so here, it may be confusing. Try and think of it in this way that if you put a mirror on your face, okay, you will see that the reflection of the mirror on your face is on the other side. So it's the same thing as asking, why is that side of my reflection on the same side as the other half of my face? It's not the same reflection. It's not the same part. Is that what you are asking? So this blue part is not the reflection of this one. This blue part is the reflection of this green part. So the mirror cuts the image. That's why they are on the same side. But it's not, what is being reflected is not the same as that one. So this green one is reflected over there, and this blue one here is reflected over there. Okay.
So ma'am, that only applies if it's log to base of or anything below 1.
What applies to anything below 1?
The one you just did. Because if you look at the first one.
You say the colors when you say first one. Which one do you mean? Oh, you mean first example or what?
Yes.
What were we sketching in the first example?
The one we did of 2 to the power of x.
Yes.
You reflected in it on the other side.
Yes, because it wasn't cutting the mirror. The mirror was not touching the image. That's why everything had its own side. So just like you, if I give you a mirror and you're looking at the mirror, it's in front of you, your reflection is not touching the mirror. But with this one, half to the power of x, it's cutting the mirror. The mirror is cutting the image. So one part will be on one side of the mirror like that.
Oh, no, I see.
Yeah. Okay. Okay. Mike muted, please. Okay. So somebody's music in the background, please. Just mute your mic. Okay, so question 4, this one is from your notes. I said question 1 and 2, you can go and do them as homework. We can look at it on Monday. And then question 4, you are given y is equal to log k base x. Y is equal to log base k of x. Now we have to determine if the graph passes through a specific point. Now to determine whether, oh no, it says determine k if it passes through a specific point. Now what that just means is the coordinates. I'll do the first one and then the other two you can do at home. So this is 3, 1. Now we're asked to find the value of k if this graph here passes through the points. Now you know that if a point lies on a curve, it must satisfy the given curve. So that means when I substitute this x here and I substitute the y over there, that equation must hold. Okay, and then I just solve for k. So to do that, this is question 4, the first one. So I will substitute y. I get 1 is equal to log base k. K is unknown, so I have to solve it. And then x, this is just the x and the y coordinates. So x over here is equal to 3. Okay, then I solve this. I write it in exponential form. This is the same as base. Exponent is equal to argument. So I have k to the power of 1 is equal to 3. This means k is equal to 3. So that's how I will solve that one. So 4.2 and 4.3, you must do them in the same way. You are given the value of x and y, and then they're just saying solve for k, in other words. So when we say a graph passes through through that point, it means when I substitute those x and y coordinates in there, then the equation is satisfied. Okay, so that's it on exponential and logarithmic graphs. The best way to really get it is to just look at examples that we have, do the questions in the book, and I think it'll be clearer. If not, you can always watch this video again, try and follow what I did. Then the last part of logarithms is transforming curves into straight lines. Now what we should know about straight lines is that if there are no questions, then I'll just move on. Okay, now what we should know about straight lines is that they are always in this form. You have y is equal to mx plus c. So you plot this on the y-axis, this is your gradient, you plot this on your x-axis, and then that is the intercept. Now you can transform some curves into straight lines by using logarithms. So if you have the notes, we are now on 3.7.5. So if I have this y is equal to kxb. Now this is an exponential graph, and the way it looks, or the way it's going to look, is also it's also going to look something like that. So this is the x, and let me draw the x. So this is what it is going to look like. This is y is equal to kxb. Okay, except now the point of intercept is going to be k, because it was supposed to be 1. Then when I multiply by k, it now changes to k. So it's like you multiply every point that you have by k. So this is just the general curve, and then at each point you multiply it by the coefficient over there. Now we can transform this into something that looks like a straight line, and we do that by taking logarithms on both sides. So I have y is equal to k x to the power of b. Now if I take log on both sides, you see I have log y. This is equal to log k x b, and then I can use my laws of exponents. This is log k plus b log x. So when I put the plus here, let me just do all the steps. This is log x to the power of b, then the b will come down. So I have log y. This is equal to log k plus b log x. Okay, so already I'm sure you can see this resembles a straight line. Now if on your graph you decide to plot this on your y-axis, let's say this is a capital Y. Now this one, log k, k is a constant. So when I take log of k, I will get some other constant. Okay, so this one I can call it a capital C. Okay, and then here this is just some constant, some number, so I can put b, and then I make this my x. So this is in the form, maybe let me use m. This is in the form y is equal to mx plus c, because I have some function of y that will go on the y-axis, some function of x that will go on the x-axis. I have a constant, a number. B here is a number. It doesn't depend on x. It's a constant. So that is my gradient. And then this one over here that has nothing to do with x and y, that is my intercept. So if I want to plot the line, the graph y is equals to k xb, as a straight line, what I must do is plot log y is equal to b log x plus c. This, when I plot this, I will actually get a straight line. Okay, the next one is if I have y is equal to k b to the power of x. Okay, now with this one here, again, I will take logs on both sides. Now, when you take logs on both sides, what you're trying to do is you want something y is equal to m, which is a number that doesn't depend on x, which is a function of x, plus some constant. That's what you want to do. So if I take logs here, I have log y is equal to log of k b to the power of x. Now this one over here, this is log y is equal to log k plus log b to the power of x. So this is log y log k plus x log b. Now here you just need to identify what is my y in this case. Now the function that has y, that is going to be your y, so this is my y. Now the constant that doesn't have an x or a y, that is your c. So this one over here, this will become my c. Then my x, the function of x is just the x by itself. Okay, so plus this one, the small x becomes big X, and then log of b. Log of b doesn't depend on x, so log of b, that is your m. Okay, so here I will have to plot log of y against x, and then I will get a straight line. Okay, so that is basically what we're doing, because straight lines are easier to understand, so sometimes we like to do that. Okay, we look at the example that is there in your notes, example 1. We are given the relationship between a and x. So we have a is equal to k, p, capital P, to the power of x. Then there's a sketch over there in your book. So there's a sketch, and the sketch is of a straight line. So here it says this is 2.5, and over there is a 9. So we are told that the relationship between a, so they've drawn, this is log a, and this is x. So on the y coordinate, they've drawn log a, and then on the x coordinate, they've just used x. They've just used x as it is. Okay, so we have to work out the values of p and k. So first thing we need to do is apply logarithms. So I have log of a. This is equal to log k p to the power of x. Then what I do, I expand on the right hand side. This is log a, this is log k plus log p of x. Then this is log a, this is log k plus x log p. So you can see this is your y. This value over here, this is my c, because it doesn't have a or x. So on the graph, you look at the graph, on the y-axis it's log a, so a is like your y here, and it doesn't have y, it's a constant. And then I have x and then log p, that is like my m. Then I know that if I look at the y-intercept on the graph, you can see the graph is drawn. If I look at the y-intercept on the graph, then I know that the y-intercept is equal to log k, and then I can solve that to get k. And then after that, I can work out the gradient. Then when I get the gradient from the graph over here, then that gradient I will equate it to log p and then just solve for p. Okay, so it's that simple. So what I do is I look at my graph. If I look at my graph here, the y-intercept is 2.5. So it's drawn over there, it's 2.5. So I have this c is equal to log k, and c is equal to 2.5. This is equal to log k. Now I solve for k. So the base over here is 10. So I have k is equal to 10 to the power of 2.5. And that's it. And then after that, this you can work it out on your calculator. I like to leave things to 3 decimal places. Say 10 to the power of 2.5. This is equal to 316.228. That is the value of k. So first thing I always have to do is change the relationship that I am given. So I'm just going over what I did before I solved the other one. So if I look at this relationship, it's exponential, but the graph that I have drawn is linear. So I went from exponential to linear. So that means I must first transform this exponential one into a linear function. And I did that by taking logs and then writing it in the form y is equal to mx plus c. Then looking at my graph, I just identify which one is my m, which one is my c. M and c, or c at least, is very easy to identify from your graph because that is just the y-intercept. You can read it from the graph. There it is. Okay. And if you know what c is also equal to log k. You solve the equation, and then that is what I get. Then m I can also use the graph that I am given. I'm trying to scroll up. M, I also use the graph that I am given. So this is the graph that I am given. I have 2 points. I have this point over here. This point is 0, 2.5. And this point over here, this is 9, 0. So I have 2 points. These 2 points, I'm just reading them from the graph. So 0, 2.5, and then 9, 0. Then I use these 2 points to work out the gradient. So you know the gradient is just delta y over delta x. So any straight line you have, the gradient m is change in y over the change in x. So you work this one out. This is 2.5 minus 0 over 0 minus 9. So 2.5 minus 0 is just 2.5. 0 minus 9, that is negative 9. Then when you divide the two, leave it as a fraction, you get negative 5 over 18. So it has a negative gradient, and you can see from the drawing, what is that? Okay, I don't know where I put it now. Okay, yeah. From the sketch, this line is decreasing. Okay, so it makes sense that my gradient is negative. Then remember what the gradient is in our equation. Our gradient over here, m, is log p. So log p is the value of the gradient, and log p is equal to 5 over 18. So I have log p is equal to 5 over 18. So avoid rounding off too early in your calculations, because if I had taken the decimal 2.778, it is more than likely going to affect my answer for P. Okay, so just leave it as a fraction because that is exact. And then what I do is I now rewrite this. P is equal to 10 to the power of 5 over 18. This I just do on my calculator, 10 to the power of 5 over 18. And this gives me 1.895. Okay, and then I am done. Are there any questions before I move on? I think maybe there are some questions.
Yes.
Yes, please ask
Isn't
your
it
question.
supposed to be negative 5 over
Yes,
18?
negative, negative, thank you. Negative, negative. So this should be 0. That is correct. 0.527. So this should be negative. Let me write it nicely. Negative 5 over 18. Yes, you're right. Okay. Any other questions? Or are we fine now? Everything is clear. Okay, so if everything is clear, let's move on. Then the next part of the question says we have to find A when x is equal to 10. So remember we have the relationship. We say that A is equal to K P to the power of x. We solved for K and we also solved for P. Now we just need to substitute the value of x. So A here will be equal to the value of K we got. Scroll down. We got 316. Let me show you over here. There it is. That's the value of K that we got. So 316.228. And then the value of P we got, there it is. Okay, 0.527. And then P has the power x, which is 10. Now this one you just calculate it on your calculator. And let me do that. At 316.228 times 0.527 to the power of 10, I am getting 0.523, okay, as my value of A. I hope that is what you are getting as well. Okay, do we have any other questions?
Ma'am, please
Yes.
explain how x is equal to 10.
It's given in the question. It says find A when x is equal to 10.
Oh, okay. Thank you, ma'am.
Yeah. Okay, any other questions? Okay, so if not, then question 2, it's example 2. I'll write it here. I would like you to just try it. The minutes that we have, you try it and then you can compare with the example. It's important that you try it on your own, then you're able to understand. So we have A is equal to K XP. So this is the relationship between A and X. So they went ahead and found a line to represent all this information, and then the line that was drawn is this one over here. So this becomes log X, and this axis here is log A. Then the line passes through the point 3 and also through the point 8. So this is also an example in your book, but this is the relationship you start with. Then you make it linear by taking logs on both sides. Then you identify this will be on the y-axis, so that's the one relating to a, and the one relating to x, that is going to be on the x-axis. The term that doesn't have a or x, that is your c, and then the constant that is multiplying the function of x, that is your m. Okay, so the questions are similar. Let me write them down. First thing you have to do is find p and k. So work out what is the value of p and what is the value of k. And then the second one, similar to the one we did, you have to find a when x is equal to 10. Okay, so we have about 8 minutes, so can give you 4 minutes. Try it on your own. Don't look at the answer in the book, just try it on your own, and then we'll see if you're able to get it. To where I found, do you all copy the question before I scroll up? But I'm sure you're even able to take a screenshot, whether it's on your phone or laptop or anything. You should be able to take a screenshot of the question. Let me see. Somebody said where I found P. This is where I found P here. Where is AKP coming from? I think that's the question. You're given that in the question. So it seems a little bit tricky, but it's not. I think sometimes you just need time to think, oh, okay, it's not very difficult. So bear with me. So again, this is the question. The very first thing you need to do is make this linear. And the way you make it linear is by taking logs. Seriously. The way you make it linear is by by taking logs on both sides. Then you separate. The one with a is the one that is going to go on your y-axis. The term with x, that is going to be the x-axis. Okay, are we managing somehow? Okay, that's good. Okay, let us just very quickly go over it. Later on, you can always go back to your notes. I'm trying to scroll up. You can go to the notes and then see how it's done. Everything is written there. So I just wanted to go over the examples. Okay, so this is A is equal to, let me put it up here. Okay. Okay, so we are told that is the relationship between A and X. So we want to make it a linear relationship between the two. So what we do is we take log on both sides. So we have log A. This is log K P X, like this. Then we use our laws of logarithms over there. So we have log A. This is equal to log K. And I hope by now you know how I got, am I doing the right question here? Okay, I don't know why they plotted. This is log X log P. Sorry, the question, I did not write it correctly. That's why. This is X P X of P. Okay, then I hope you know by now how I get P log X. Okay, so we said on the y-axis we must put some function that has to do with A, and on the x-axis we must put some function that has to do with x. So on this side, this is the function that has to do with A, so this will become my y. Now this one here has nothing to do with A or x, so this will become my intercept. So when I work out the intercept, I equate it to log K. And this one over here, log X, is a function of X. So that will become my x-axis. And then P is the one that is multiplying the function of X. So whatever is multiplying your function of X, as long as it doesn't have an X, that is your M, your gradient. So now I see it is linear now. It's in the form y is equal to mx plus c. Then I have to work out k and p. So I start with the intercept because that is easy to see from the graph. So on the intercept, on the graph, my y-intercept is 3. So I have c is equal to 3. This is from the graph that I drew up there. Okay, but I also know that the intercept is equal to log k. So log k is equal to c, which is equal to 3. This means that log k is equal to 3. Then to solve for k, the base here is 10. I have k is equal to 10 to the power of 3, which is just 1000. Then I need to solve for p. P here is the gradient. I don't need to take logs or anything of that because the value of p that I get is exactly equal to my gradient. So I have the coordinates of the intercept. I can use them to work out the gradient. So my gradient, which is the value of p, this is just delta y over delta x. And I use the points given on the graph. So the first point is 0, 3. The second one is 8, 0. So the 2 points right from here, it's 0, 3, and then I have 8, 0. So to find the intercept, delta y over delta x, so it's 3 minus 0 over 0 minus 8, and this is just negative 3 over 8. So that is my value of p. Okay, so I'll leave it like that just to be accurate. So then I can always rewrite the equation of the relationship between a and x. So it was like this: a is equal to